You very much for your introduction. First I have to get acquainted. Today I want to talk, as I said, about silicon cell silicon cell inspection. First of all, I want to tell you a bit about VITRONIC and what is VITRONIC doing in PV. Then I will split into wafer inspection and cell inspection, and then I try to summarize the main aspects for high efficiency cells. First, go to does that work? Okay, I'll use that here. Tell you some about VITRONIC. VITRONIC is a privately owned company with more than 400 employees. The head office and the design and the production facilities are in close by Wiesbaden. Besides different sales offices, we have quite some subsidiaries around the world. The newest one is now in China, in Shanghai. VITRONIC is one of the first machine vision companies founded in 1984. We are continuously growing without acquiring any other company. All our software and quite some of the hardware are made by VITRONIC, by us ourselves. We do not deliver components, but solutions for the customer's tasks. We have divided the company now in 3 divisions, into the industry, the logistics, and the traffic technology division. Within the industry division, photovoltaic was dominant for about 5 years now. It decreases at the moment a bit. We will see how it develops again in the next years. But besides photovoltaics in the industry department, we also have applications in the automotive and in the pharmaceutical and medical departments or areas. So we do not get out of work. In the logistics, the other division, the second division, we develop and sell camera systems for identification of goods. Many thousands of them are integrated in postal distribution centers worldwide. In the traffic division, then we produce camera systems for tolling and for vehicle identification, and also for speed enforcement. But many people do not like too much. I not either. At the toll collect gantries along the German autobahns, all those gantries are from VITRONIC, so everyone has passed already one of the bigger installations of camera systems from VITRONIC. VITRONIC and PV. Meanwhile, quite more than 1,000 VITRONIC systems enable highly automated cell and module lines worldwide. I can say that all big cell production sites that produce without manual visual inspection, they all rely on VITRONIC systems. In fully automated lines, up to 10 WinSpec solar systems are integrated behind each other or within such a line. In all relevant steps, the systems are integrated in wafer inspection, in texturization, after coating, after metallization, then of course in the final cell inspection, then in a module production, the string inspection, pre-laminate and laminate inspection, the frame, the box, and the final module inspection, often combined with electroluminescence. Okay, so much for VITRONIC and what we are doing in PV now, especially for going to wafer inspection. Wafer cameras are integrated in final inspection of raw wafer lines and also for incoming inspection at cell lines. These are systems for classifying and sorting into classes besides the classical tasks of geometry, measurement, edge detection, surface inspection, and microcrack inspection, now also topics are granularity and crystal fractions, and of course also photoluminescence. Crystal, first of all, silicon becomes transparent at wavelengths above 700 nanometer, and microcracks can be contrasted with infrared backlight. Here are some samples for microcrack. Well, I'm in the wrong. I just have to switch because this is a short version. And sorry, but we have to go back because I did not want to skip all these. Where is it? Can someone help me, perhaps? VITRONIC, is that here? No.
Yeah, you have that VITRONIC file. The last file is VITRONIC.
No, that's old. That's not it. That's not my... No, wait. Where is that stick? I have to find this stick. Yeah, this is the right one here. Okay. Here we were. Sorry. Because I wanted to show you these slides too. This is where silicon becomes transparent at wavelengths above 700 nanometer, and microcracks can be contrasted with infrared backlight. Here are some examples for microcrack detection. And now, today it's also necessary to not only reject wafers with cracks that are not relevant for efficiency and cell survival, like cracks like this. You have to determine cracks that are really interesting for survival of the cells. Okay, just mixed a little bit. So now, at cast monowafers, it's crucial how big the monocrystalline part is in order to choose the best fitting processing. That also can be detected, besides microcracks, with the same camera system. I hope you can see that. How does that work with a... Yeah? Oh yeah. You see this outline is outlining the monocrystalline area. And also the granularity is a topic, not only for cast monowafers, but also for cast monos. With a granularity mapping algorithm, bad areas can be trapped and classified. I don't want to go into the very details, but we can talk about it later. Who is interested in these details? New challenges came up with the diamond wire cutting. The surface is much more structured, and direction invariant imaging needs special precautions. A short excursion to photoluminescence. Photoluminescence has the potential to tell more about local efficiency and bad areas, but up to now it's still not widely spread and still very expensive. I don't want to get in these details either. VITRONIC is working on systems like this, but we do not provide this technology yet. Now I'll tell about systems along the cell production. Camera systems, meanwhile, are integrated after almost every production step. Except in the cell tester, the camera systems are monitoring the processes and create warnings or stops when process is leaving or tends to leave the tolerance levels for best quality. In the cell tester or sorter, the quality values of the cameras are combined with the flasher values to a qualification level and sorted into appropriate bins. The different steps are after texturization, after coating, and after printing, and of course the final cell inspection. First step, texture inspection. After applying the nanostructure to the sunny side, the local reflectivity properties can be monitored with line scan cameras and specially adapted illumination. Drifts and deviations can be detected and reported. After anti-reflex coating, anti-reflection coating, not only color deviations can be monitored with a color camera, but also the layer thickness can be calculated. The color values correlate with the layer thickness. This way, the layer thickness can be evaluated within about a nanometer accuracy. Some cell producers prefer spectrometers for layer thickness measurement. Some even use both methods in the same line. Especially multi-layer technologies require different solutions for thickness measurement. Their spectra often have more than one minima. These are also challenges for spectrometers. After print inspection, systems earn their money by extending the lifetime of screens to their real end, and also by not producing scrap at all or hardly any scrap. Print inspection is becoming more crucial with thinner grid design, with double print, selective emitter structuring, there sometimes also before metallization, metal plating and metal dispensing. For thinner grid, higher resolution images are needed. VITRONIC, we provide a standard line scan device with 8K line that scans an image of 64 megapixels. That means 20 micron resolution that in the most cases is sufficient also for thin grid inspection. Here are some screenshots of typical deviations. Here you see a gap and a widening of fingers. And when it comes to very fine grid metallization, even higher resolution may be required. Here a comparison, fine grid to regular print. Well, the print here looks ugly because it's overexposed, but it is taken with the same property in the same image. And the resolution is in the range of 3 micrometer. Selective emitter is a challenging topic for contrasting too. Selective emitters can be contrasted by using the differences in surface topology or using the reflection differences of differently doped areas in the further infrared region. Because of the poor contrast between differently doped areas, traditional vision systems are not efficient in pattern alignment over SE. Here you can see, for example, when you do it standard, you have a contrast. With little changes of the parameters, you don't see it anymore. And these are physical, where it is, where it is checked in the infrared range above 1200 nanometers. Now to backside print. Normally resolution requirements are less than on front side. It proved to be a big advantage that VITRONIC systems can evaluate 3D properties by taking several images with differently directed illumination. Here you can guess the effect. These are the different illuminations, and this is finally what can be seen. I do not see if you even can see it from there, but here on my monitor it looks quite good. Higher resolution is needed also for MWT and EWT cells when they have laser-scribed insulations, like here and here also. In contrary to the systems I just explained, the cameras in cell testers are quality sorters, same as the wafer systems I explained in the beginning. They classify into different bins, into different color and quality classes. In Asian production lines, often the only camera systems at all are integrated in the cell testers before the flasher, and often only for the front side. Let's see if that works. Does work, doesn't matter. Biggest challenge at high efficiency cells is the immense contrast between almost non-reflective active surface and highly reflective silver print. A very smart and economically priced system is our color line scan system. You also can see it on our booth. The trick is the sensor chip with 4 separate receptors, 3 for the color, red, green, blue, for excellent color sensitivity in the dark surface, and a separate black and white sensor trimmed for the high reflectivity of the metallization. So this in one imaging and one scan provides 4 times 16 megapixel imaging. Here you can see some of the standard defects that can be seen when evaluated properly in the color range, or here too. And of course, here you see the print is not all white, but it is in decent gray levels. You really can see also about something like the topology. Challenge for cell producers with different production plants in different countries is that they need to normalize classification and color sorting. And for that, color calibration tools need to be created, and we have done that with special wafers where cell fragments that were measured with ellipsometers are integrated, so you can make out of one original wafer or cell, you can produce up to 18, 20 equal calibration tools. Finally, some aspects about electroluminescence. EL needs contacting, and contacting is only done once in the flasher. Separate stations have not succeeded to be integrated more than as trial units. But flasher companies like Halm, they have it in their repertoire. There it makes sense to integrate directly into the flasher. VITRONIC has integrated already more than 50 EL systems, but only into module lines, because we do not have the access into the flasher. But modules are not topics for today. Here's just some characteristic defects to be detected in electroluminescence. Talking about today's system requirements also should include some aspects about the software. Since, since production plants are more in Asian countries now, and an easy to use interface becomes more and more crucial, In big production lines, data mining and MES are also progressing. Only with good calibration and self-monitoring, high quality can be maintained. So I'm coming to the conclusion. These were my topics. I explained wafer and cell inspection requirements for modern high-efficiency cells. New for wafer inspection are the demands from diamond cut, granularity, and crystal fraction, and not to forget a smart microcrack detection. For cell inspection, I mentioned the process optimization tools for texturization and coating, the high demands for fine-grit metallization and complex back coating, the special methods for selective emitter, and the high dynamic and resolution demands for final cell testing. Thank you for your attention. Waiting for your questions.